All right, so we're going to look at a couple of examples working with the concept of and multiplying fractions and a direct application of multiplication of fractions. All right, so let's start with this one. So illustrate 2/3 of 4/5 on a number line. So I want to find 2/3 of my new unit 4/5, right? So we know I need to break that into 3 pieces and take 2 of them. But what is 3 pieces of 4/5? So let's look at a number line quick. So I know I made my unit really big, but I took the original unit, and 4/5 indicates that I broke it into 5 pieces. 1, 2, 3, 4. And I took 4 of those, right? So each piece is 1/5, 2/5, 3/5, 4/5, and then 1 is 5/5. So my starting unit is this right here. I got 4/5. And I want to take 2/3 of that. So we know that I need to break 4/5 into 3 equal pieces. But what is the size of each of those thirds, right? What does it look like to break 4/5 into 3 equal pieces? I know I would put it, I don't know, maybe somewhere right around here and here, maybe, I'm guessing, right? That's kind of hard to figure out, but luckily we know what equivalent fractions is. I can take 4/5, multiply top and bottom by 3, right? Multiplying on the bottom breaks 4/5 into 3 pieces, and I know that total I'm going to have 3 pieces, right? So I'm taking 3 of those. So we're going to look at this a little bit strangely. 5 times 3 tells me that there's going to be 15 total pieces, and to get the whole, I'm taking 3 of those. So I have 4 15ths plus 4 15ths plus 4 15ths, and that gets me 12 15ths, and we know if we reduce that, we'll get back to 4/5. So why is that important? What does that tell me? If I take 4/5 and break it into 3 equal pieces, each of those equal pieces is a 4 15ths, right? 4 copies of 15ths. So if I take each one of my fifths now and break it into 3 pieces, then 4/5 represents one of those pieces. So I have 1, 2, 3. Here's 4 15ths. I was close. 1, 2, 3, 4. Here's 8 15ths. And 1, 2, 3, 4. Yeah, there's 12 15ths. There we go. So I have my 4/5 broken into 3 equal pieces. 4 15ths, 8 15ths, and 12 15ths. And what I wanted was 2 of those 3 pieces. Well, here's 1, 2. So 4/5, 2/3 of 4/5, or 2/3 times 4/5, we know is equal to 8 15ths. And again, that leads to the simple algorithm of just multiplying straight across. 2 times 4 gives me 8, and 3 times 5 gives me 15. But this is the y, right? Breaking it down, multiplying by 2/3, that tells me I'm breaking that current unit into 3 pieces and taking this number of them. All right, so let's say that, I don't know, we go to some gathering, so some social gathering. Can't even talk about it. I don't remember what that feels like anymore. But let's say there's 20 people there. And my family makes up 1/5 of the people there. All right, so we have 20 people at the social gathering. My family makes up a fifth of the people there. So how many people there are members of my family? Well, my family makes up 1/5 of the people there. And so we looked at that concept of multiplication. So 1/5 of the people there, I'm looking at 1/5 of the people there was 20. And we know this means 1/5 times 20. So again, by definition of fractions, this means I'm taking my whole, all 20 people, I'm breaking it into 5 pieces, and I'm going to take one of those pieces. So if I take 20 and break it into 5 pieces, each piece contains 4 people, or each group, right? By our definition of division, I'm breaking it into 5 groups. Each group would have 4 people, and I'm taking one of those groups. So that gives me 4, right? And by that algorithm, we see 1/5. I need to multiply top times top, bottom times bottom, so this would be 20 over 1, and multiply straight across. 1 times 20 is 20, 5 times 1 is 5, and now this looks just like our whole number division. 20 divided by 5 gives me 4. So either way, I get 4. All right, so what is a direct application of the way we can multiply fractions now? Well, I will tell you, just in case you don't know. It's multiplication or multiplying decimals. And it's very similar to the way we added fractions, and we used that to see how we could explain the algorithm for adding and or subtracting decimals. Same exact thing here for multiplying decimals. So if you think of the algorithm, let's do an example real quick. Let's say I want to do 2.35 times 1.7. So the algorithm for multiplying decimals tells me just disregard the decimal point for right now. I'm looking at 235 times 17 essentially. And I'm going to multiply this. We did this. We've done this several times. So I'm going to start with my 1, multiply it times everything in the top row, and then I'll do the same thing with the tens, which happens to be a 1, and multiply that times everything in the top row and add. So 7 times 5 is 35, carrying my 3, it's 21, so 24, carrying my 2, I get 16, 0, 5, 3, 2, right? 5, 4, yes, all those things. So add them together, I get 5,993. So 3,995. So the algorithm then gives us a way to figure out where the decimal point goes. It tells you to go back, just add up the number of, the amount of numbers to the right of each decimal. So I have 1, 2, 3, and that's how many decimal points your answer will have, or how many numbers to the right of the decimal your answer will have. So I should have 3, so 1, 2, 3 should all be behind the decimal, so I have 3.995. Now the question is, why? I mean, that's a nice little shortcut, which is what the algorithm gives us, but that doesn't tell us why. So let's do this with our handy dandy decimal fractions. So 2.35 as a decimal fraction, we know to be 235 over 10 squared. And 1.7 as a decimal fraction, we know is 17 over 10 to the first, and we want to multiply this together. Well, we just looked at multiplying fractions, and I am going to use the algorithm here for sake of time. This tells me, the algorithm for multiplying fractions tells me that I can just multiply straight across. I do not need a common denominator because I am just multiplying. So 235 times 17, just like they are whole numbers, because they are, we know that gives us 3,995. And 10 squared times 10 to the first, this is 100 times 10, which is 1,000, so that's 10 to the third. Now, without having to convert, right, if I had 10 to the 7th and 10 to the 5th, I don't want to have to convert that to whatever 10 to the 7th times 10 to the 5th and actually multiply that. So we do have exponent rules. When I'm multiplying with the same base, I can just add the exponents, right? So 10 squared times 10 to the first does give me 10 to the third. And what is significant about that, again, we understand decimal fractions, so this indicates how many decimal points I will have, or how many numbers to the right of the decimal I will have, and I should have 3, so 3.995, which is exactly what we get when we use the algorithm for multiplying decimals. So let's do one more by that token. So 6.7304 times something like that. So 6.7304 times 5.029. So before I actually multiply this, how many numbers to the right of the decimal will the solution have? All right, most likely you just count it up. 1, 2, 3, 4, 5, 6, 7. We know the solution will have 7. Could you explain it, though? So the explanation for why this will have 7, just counting the decimals, or the numbers to the right of the decimal, is not an explanation. That's a neat trick that is set out by the algorithm. Why is it that we will have 7 decimal places? So again, that goes back to our decimal fraction, so we're going to do this in the same way. 6.7304 as the decimal fraction is 67304 over 1, 2, 3, 4, 10 to the 4th power, times 5.029 as the decimal fraction is 5029 over 10 to the 3rd. So I have 10 to the 4th times 10 to the 3rd, right? Just using my algorithm for multiplying fractions. 10 to the 4th times 10 to the 3rd. I know I'm going to end up with 10 to the 7th. If you need to multiply that out, that's fine. 10 to the 4th means 1, 2, 3, 4, and 10 to the 3rd is 1,000. So if I multiply that out, I'm going to end up with this right here, which is 10 to the 7th power. 67,304 times 5,029 is a number. I am not using a calculator. I get 338471816. Totally just did that in my head. And we know the denominator is 10 to the 7th power, and by our decimal fractions, we know that means that this number as a decimal will have 7 numbers to the right of the decimal point. So 1, 2, 3, 4, 5, 6, 7 will all be to the right of the decimal point. So I'll have 33.84711816. There we go.